Morning, friends. Myself, Vijay Shankar from ECE Department, Civil Engineering College. Today, we are going to discuss about the energy density in electrostatics or electrostatic fields. Energy density in electrostatic fields. See, when a unit positive charge is moved from infinite to a point in a field, the work done by the external source and energy is expended. Suppose you can assume here the figure is there, a space. First you can place a charge Q1 at the point P1. Consider a space here. Place a charge Q1 at the point P1. There is no work done at this here. And another charge Q2 is placed at the point P2, or you can say the test charge sureties. Then a force is exerted. Due to the charge placed at the P1. Then another charge Q3 from the infinite you can place in the space at the point P3, and there is a force is exerted on Q3 due to the Q1. Here there is a Q3 is there, and Q1 and Q2, not the Q1, that is a Q2, sorry, and Q1. Whenever you can place a Q3 charge at the point P3, the force is exerted due to the Q2 and due to the Q1 also. When we are placing the charge Q1 at the point P1, there is no any other charges in the space. So there is no any work done, occurs, no work done. Whenever there is a Q2 is placed, brought from the infinite, and you can place at the P2 point, a force is exerted due to the Q1. A force is exerted on Q2. A force is exerted on Q2 due to the Q1. And similarly, another charge, the Q3 is placed at the point P3. A force is exerted on the Q3. A force is exerted on the Q3 due to the Q1 and due to the Q2 also. Q2 and the Q1, both. Following my students. So same here. If the external source is removed, then the unit positive charge will be subjected. A force is exerted by the field and will be moved in the direction of the force. Okay. See here. Consider an empty space where there is no electric field at all. Consider the empty space where there is no electric field at all. The charge Q1 is moved from infinite to a point in the space P1. A charge Q1 is moved from infinite to a point in the space at the P1. This requires no work as there is no E bar present. This requires no work as there is no E bar present. Means there is no any charge inside, only the Q1 only. Now the charge Q2 is to be placed. At point P2 in the space as shown here. But now there is an electric field due to. Q1 and the Q2 is required to be moved against the field of Q1. Hence the work is required to be done here. So for the potential is equal to work done per unit charge W by the Q. The potential V is equal to work done per unit charge. Okay. The work done is equal to, then the equation becomes work done is equal to the potential V into Q. See, work done to the position Q2, whenever the Q2 is placed at the point P2, the potential due to the Q1, the force is exerted on the Q2, so V21 of Q2, where the V21 is a potential at P2 due to the P1. Means the force is exerted on the Q2 due to the Q1. Okay. Now let charge Q3 is to move from the infinite to the point P3. There are electric fields due to the Q1 and the Q2, hence the total work is done to the potential at P3 due to the charge at P1 and due to the potential at the P3 due to the charge at the P2. Potential at P3 due to the charge P1 and potential at P3 due to the charge at the P2. So now the work done to the position of Q3 at P suffix 3 is due to the Q2, the potential V32 of Q3 plus due to the Q1, the potential V3 of 1, the Q3. Okay. V21 is a potential at P2 due to the P1, and V31 is a potential at P suffix 3 due to the P1, and V32 is the potential at P3 due to the P2. Okay. So suppose if we get the Q4, the charge Q4 is placed at P4 due to the Q3, due to the Q2, due to the Q1, the force is exerted on the Q4. So the potential is, or the work done, the potential V4 3 on Q4 plus V4 2 on the Q4 plus V4 1 on the Q4 is a potential at point 4 at P4 due to the P1, potential at the P4 due to the P2, and the potential at P4 due to the P3, and so on. Got it, modest students? See, thus for the charge Q1, Qn to be placed at the Pn, we can write it as so P2, P3, P4, and so on. If it is a Pn, the work done, the position Qn is at the Pn is V N1 Qn, B N2 Qn, N3 Qn, and so on up to. Got it? So first of all, you can keep assume that empty space and there is no any field is there in the space. No work done occurs to Q1, and you can bring the Q2 from the infinite and placed at the P2 position. There's a force is exerted due to the Q1. The work done is potential into the charge due to the potential at the P2 due to the P1. Okay, so the work done at the position Q1 at the Pn is N1B, N1, B, N2 of the Q1, means the charge Q1 exerted a force due to the charge Q2. The force is exerted on the Qn due to the Q1, and so on. Hence, the total work done in the position of all the charges is because we assume a space at the P1, at the P2, and at the P suffix 3. Q1 is a charge, and the Q2 is a charge, another charge, and the Q3 is another charge you can place. The total work done in the positions, VWE is Q2. If the Q1 is placed at the point P1, there is no any electric field and there is no any potential done and there is no any work done occurs. When the Q2 is brought at the P1, P2 position, then only there is a force is exerted, electric field is produced, and the potential is there and the work done occurs. So the V21 Q2 plus, and now the Q3 V31 due to the Q3 and V32 Q3 and so on. This is the equation we got when the Q2 is placed at the point P2 and the Q3 is placed at the point P suffix 3. So when the Q3 is there, due to the Q2, due to the Q1, there is a force is exerted. When the Q2 is there, there is no any Q3. Before that, there is only the Q1. There is a force is exerted on the Q2 due to the Q1. So W is equal to Q2 V21 plus Q3 V31 and Q3 V32 and so on. The total work done is nothing but the potential energy in the system of charges. Hence, it is denoted as WE. Hence, it is denoted as WE. Again, see, if the charges are placed in reverse order, we can write it as. So previously, we can assume a empty space. First of all, you can place the Q1 at the position P1. Then after, you can bring the Q2 and place it at the point P2. Then after, you can bring the Q3 and place at the position P3. Now you can continue the process with the reverse order. Suppose there is an empty space here. First of all, I place a Q4 at the position of P4 here. Now there is no any work done. No work done because there is no any field is there in the space. Work done. Now, from the infinite, bring the Q3 and place at the position P3. A force is exerted on the Q3 due to the Q4. A force is exerted on Q3 due to the Q4. Now, What is the work done here? The work done to the position Q3 at P suffix 3 is equal to V3 of 4. V3 of 4, and the charge is here now the Q3. Charge is the Q3. Now, then bring the Q2 charge and place at the position P2. Now, a force is exerted on the Q2 due to the Q3 and due to the Q4. Now, what is the equation we have to get? Q2 at the position P2 is equal to. So, a force is exerted on the Q2 due to the Q3 and due to the Q4 also. So, V2 of 3, when we keep the charge Q2, plus V24, when the charge is kept at the position, charge Q2 is kept at the position P2. So this is another equation. And then now I bring that Q1 and place at the position P1. A force is exerted on the Q1 due to the Q2, due to the Q3, and due to the Q4 also. So what is the equation we get? Q1 at the position P1 is equal to, here the V1 due to the Q2, there is a force is exerted and the work done, potential is developed, potential is there, and the work done occurs, plus V1 due to the Q3, when we place the Q1, and V1 due to the Q4 when the charge is placed at the position P1. So now I can add all the terms, the total work done. The total work done is V12 Q1, 13 Q1, 14 Q1, and V23 Q2, V24 Q2 plus V34 Q3. Got it, my students? These are reverse order. Understood? Now you can add all the terms. Now you can add all the terms, the reverse order and the forward order. WE is equal to. So previously we got this equation WE is equal to. Now in the reverse order and forward order, WE is equal to Q2 V21 plus Q3 V31, Q3 V2. V32. So add these two equations. Add these two equations in the reverse order and the positions in the forward order. So W2 W, the left hand side W plus W is equal to 2 WE. Let us take the Q1 is a charge is a common. See in this there is no any Q1, only we have here the Q1 is there, the Q1 V12. So V12, V13, V13, and V14, V14, and so on. If it is the V1N, up to the n number of charges you can take. Then Q2, then the charge Q2 we can take here. Q2 is equal to. What is the Q2 common? Here the Q2 is there, and here also the two terms. Q2 into V21, V21, V23, V23, V24, and V24, and so on, V2N. Already we take the Q1, Q1, and the Q1. Now it is a Q2, Q2, and here the Q2. Then take the Q3 as a common. V31, V31, and V32, V32 here, plus V34, plus up to so on, V3N, and so on. And Q4, and you can take the Q4 also, plus, let us take it as a Q4. What is the potential? The potential will get here V41 plus V42 plus V43 plus up to so on V4N. Got it, my students? So you can add the two equations from the forward order and the reverse order. When charges are placed in the empty space, the 2WE is equal to Q1 with the total potential, and the Q2 with the total potentials, and the Q3 with the total potentials. Each sum of the potential is a total resultant potential due to all the charges except for the charges at the point at which the potential is obtained. See, the Q1 is there is no any 1, 1, 1, 2, 1, 3, 1, 4, so on. When the charge is Q2, there is no any V22, V21, 2, 3, 2, 4 on. The charge is Q3, we have only the 3, 1, 3, 2, there is no any 3, 3 yet, V34. The charge is Q4, V41, 4, 2, 4, 3, and there is no any 4, 4, it is a 4, 5 will get. So each sum of the potentials is the total resultant potential due to all the charges, except for the charges at the point at which the potential is obtained. Okay. So V12, 13, 14, 12, 13, 14, and so on, V1N, assume the V1, and the 21, 23, 24, V21 is assumed the V2, and V31, 32, V34, and so on, V3N is V3. Then the 2W is equal to Q1 V1 plus Q2 V2 plus Q3 V3. And rewrite this expression. The 2WE is equal to the Q1 V1, Q2 V2, and Q3 V3 as a sum of I'm taking the values 1, 2, 3, and so on, increasing value. M is equal to 1, 2. N values are there. QM and the VM. So when M is equal to 1, Q1 V1, and M is equal to 2, Q2 V2, and so on, the M is equal to N, QN, VN. So WE is equal to 1 by 2. The sum of M is equal to 1 to N, QM into VM. There is a potential energy stored in the system of N point charges. The potential energy stored, WE is equal to 1 by 2, the sum of M is equal to 1 to N, QM and VM. Okay. Now, this is the same potential. Instead of the potential point charges, the region has continuous charge distribution. Then the summation of the equation 7 becomes, see what is the W is equal to 1 by 2 QE into, or if I use only the one equation, or I am taking the sum of the value, WE is equal to 1 by 2 Q into V. Only the one equation. Okay. Add the line charge. What is the line charge saying that dq is equal to? dq is equal to, or change of charge with respect to the length, the dl is a rho l. The surface is change of charge with respect to the surface, the charge density rho s, and change of charge with respect to the volume is rho v, the charge density, volume charge density. So dq is equal to, from this equation, the dq is equal to rho l into dl, and q is equal to integral rho l into dl. Now substitute here, the WE is equal to 1 by 2, the q replace with integral rho l dl into v. So work done, WE is equal to potential at the energy stored, W is equal to 1 by 2, the integral rho l dl into v. And when the surface is the same thing, dq is equal to, or directly I'm writing the q is equal to integral rho s into ds. And here the q is equal to integral rho v dv. Means simply apply the integral on both sides. Integral of derivative is a q1. So W is equal to, substitute the q as the charge density, rho s ds into v. W is equal to rho s into ds into v, joules, the work done. And W is equal to 1 by 2, the integral rho v dv into v. Okay, where v is a potential. Now the energy stored in terms of d bar and e bar. D bar is electric flux density and E bar is electric field intensity. The energy stored, W is equal to, we know the volume, 1 by 2, the integral rho v into v dv. Here the v is not the volume, my dear, it's a volume, my dear students. This v is a potential. Don't think that is an integral v dv. So integral v dv is a v square by 2. So this v is the potential and this v is the volume. Okay. So integral value is a rho v into v is a constant. Okay, my dear students. Consider the volume charge distribution having the uniform charge density rho v as the total energy stored is given by the W is equal to 1 by 2, the integral volume integral rho v into v dv. From the Maxwell's equation, one of the Maxwell's first equation from the gas law, we got from the gas law, Q is equal to integral d bar dot ds bar. This is surface integral. D bar dot ds bar. And convert this surface integral to the volume integral by using the divergence theorem, del dot d bar into dv, del dot d bar into dv. And here the q is equal to, in terms of the volume, q is equal to, now only we discuss that is a change of the charge with respect to the volume is a volume charge density rho v, and dq is equal to rho v into dv, and apply the integral on both sides, we get q is equal to the volume integral rho v into dv. Now this is equal to the q and this equation is also equal to the q. Comparing these two equations, integral, volume integral rho v dv is equal to the volume integral del dot d bar into d. Okay, so both sides we have the volume integral, remove that volume integral, and finally we'll get that del dot d bar is equal to rho v. So first Maxwell's equation proof by using the gas law, electric field, the gas law for the electric field. Got it, my dear students. Now I am using that equation according to Maxwell's first equation. Rho v is equal to del dot d bar. Substitute as a rho v, W is equal to 1 by 2 the volume integral del dot d bar into b dv. Here, one of the property you have to know is a vector identity. Vector identity. What it matters, friends. See, one of these property we have to know that del dot b a bar is equal to del dot b a bar is equal to, first of all, if I take the a bar dot del v, a bar dot del v plus, and the second term we have here the v into del dot a bar, del dot a bar. This is a property when the del dot v a bar, any term is there in the a, either it is a b or the j also. J, suppose it is a j, means j bar dot del v plus v into del dot j bar. Understood? So here we have the del dot d bar into v. Del dot d bar into v. So del dot a bar v into del dot a bar is equal to, so this is the equation, and left hand side we have del dot b a bar, del dot b a bar minus a bar into, not the a bar into a bar dot del v. So in this equation the same thing in the del dot d bar into v. So v into del dot d bar. Suppose if I am taking this function d bar, d bar, v is multiplied. The total function is rewrite as del dot v d bar minus d bar dot del v, d bar dot del v. Okay. Now W is equal to 1 by 2 the volume integral del dot d bar into b, del dot d bar into b is rewrite as del dot v d bar minus d bar dot del v whole multiply with dv. But v is a volume, my dear students, here because it is a volume integral. Okay. See, W is equal to 1 by 2 del dot v d bar minus del d bar dot del v. Here the del v is also there. There is some mistake is there here. Del v into d. So split this at the two parts of the integral. 1 by 2 the volume integral del dot v d bar into dv minus 1 by 2 into integral, volume integral d bar dot del v into dv. So we got the two equations, two integrals, del dot v d bar into dv minus d bar dot del v. What it matters. So here now I am using the, according to the divergence theorem, the volume integral can be converted to the closed surface integral if closed surface totally surrounds the volume. See, in the second part, integral 1 by the volume integral del dot v d bar dv is equal to v d bar dv is equal to, means it is a volume integral, is equal to 1 by 2 the v d bar dot ds bar. V d bar dot ds bar. Why it is means, see, the integral d bar dot ds bar is a Gauss law in a surface integral. We are converting this surface integral as a volume integral by taking the d bar and del dot d bar into dv. The volume integral is. So del dot, here the del dot v d bar is there instead of t, v d bar into dv. What is the surface integral now? D bar dot ds bar. Here the d bar is d bar dot ds bar. Now instead of d, here the v into d bar is there. V into d bar. So the volume integral is converted to the surface integral as 1 by 2 the surface integral v d bar dot ds bar. Don't confuse, my dear students. So surface integral is converted to the volume integral by taking the d bar and apply the dot product with the del dot d bar. Now here we have del dot, instead of d bar is a v d bar. V d bar into dv. Okay. So now it is in the surface integral v d bar dot ds bar convert the volume integral to the surface. So v d bar dot ds bar. So the first integral here is changes as the surface integral 1 by 2. The surface integral is v d bar dot ds bar. V d bar dot ds bar minus the same thing 1 by 2. The volume integral d bar dot del v into d. Got it, my dear students? So the finally the W is equal to 1 by 2. That's the surface integral. The first part I converted to the surface integral v d bar dot ds bar minus 1 by 2 the volume integral d bar dot del v. Now we know that the volume, not the volume, the potential is proportional to the 1 by r. The potential is proportional to the 1 by r. Why? The potential V is equal to Q by 4 pi r. 4 pi epsilon naught r. Its take is a constant, it's totally, the V is proportional to 1 by r. The potential at the point charge. And similarly, electric flux density d bar is equal to Q by 4 pi r square into AR bar is also there. And it is also proportional, if it is a constant, d bar is equal to, d bar is proportional to 1 by r square. Is a point charge for the point charge. And now, and so on. So, VD bar is proportional to VD bar. VD bar is proportional to 1 by r and the 1 by r square. V is proportional to 1 by r and D is proportional to 1 by r square. So, it is totally proportional to the 1 by r cube. So, the VD bar is proportional to at least the 1 by r cube, while D differential surface varies as r square and the total integral varies as 1 by r. Why it is in the previous first term of integral here, VD bar dot ds bar. VD bar dot ds bar. VD bar is proportional to 1 by r cube and the ds means 1 by r square. The differential surface. Okay, 1 by r square, or the r square it is, not the 1 by r square, r square. So 1 by r cube into r square, the dot product r square, as of ds is varies, R square and cube will get cancelled. The total term is proportional to 1 by R, the first integral. As the total integral varies as 1 by R, as the surface becomes very large, R tends to infinite and 1 by R tends to the 0. And the closed surface integral is 0 in the equation. The first integral of the WE, the first term is a 0. See, the first term becomes the 0 value. And the second term is there. But second term minus 1 by 2 the volume integral d bar dot del V into d. D bar dot del V into dV. We know the gradient of V is E bar is equal to minus del V. In the previous class, we seen the gradient V or grade V or del V is equal to minus E bar, or E bar is equal to minus del V. Substitute here D bar dot E bar. So W is equal to minus 1 by 2 the volume integral D bar dot minus E bar into dV. So minus into minus is becomes of plus 1 by 2 the volume integral D bar dot dV. So E bar and E bar into dV also the volume integral. 1 by 2 the volume integral D bar dot E bar dV. The joules is a work done. The energy stored, the W is equal to, in terms of E bar only, the 1 by 2 the volume integral, you know the D bar is equal to epsilon naught into E bar. Epsilon naught into E bar dot E bar dV. Okay, so epsilon naught by 2, the volume integral, epsilon naught is a constant, the volume integral, E square, E is equal to the work done, energy stored in terms of E only. Okay, W is equal to 1 by 2 the volume integral, epsilon naught E square dV joules. Otherwise, you can substitute the E bar in terms of the D bar. W is equal to 1 by 2 the volume integral D bar dot epsilon E bar is equal to D bar dot D bar by the epsilon naught into dV. So that is equal to 1 by square into d. W is equal to. So energy stored in terms of d and energy stored in terms of d bar and e bar, energy stored in terms of e and energy stored in terms of the d. Got it, my students? Okay. Now we can apply the differentiation on both sides. The dWE is equal to 1 by 2 d bar dot e bar into dV, or dWE by dV is equal to 1 by 2 d bar dot e bar. The change of is called energy density in electric field, having the units joules per meter cube energy density. If this is an integrated over the volume, we get the total energy present. WE is equal to, apply the integral on both sides. You'll get WE is equal to 1 by 2 the integral d bar dot e bar.